what I want to do today, I've got, what, 3 hours, you said? The usual. No. What I want to do today is talk a little bit, or a lot about the stuff behind stories and people, because I think, especially, I think for all of us, but especially students and even my colleagues, you know, you mentioned some results, but there are really, there's always really, I think, really interesting stories, how things got created and how they happened. And I'm going to do that about some older results and some newer ones. So I hope that's okay. If it's not, well, okay, well, we won't go there. So it's sort of the story behind the result, but lots of them. So the first thing I want to do is quote from a movie called The Swingers. When Vince Vaughn did this a number of years ago, it has nothing to do with swinging in that sense. A lot of you know the movie? Okay. There's an opening scene, not opening, but one of the early scenes, he's talking to his colleague, and he's saying, look at this, or you can read it. I want you to remember this face. This is the guy behind the guy behind the guy. So I think what I want to try to do today is give you some idea of some of the stories behind some of the results. And when you mentioned, for example, take grant, I hadn't planned to talk about that, but you can talk to me offline about that. There's a funny story and there's an X-rated story, which we can't put some things on the blog. So if you want to know about that, I'll be happy to talk to you. Okay, and I'd also like to do this. I was told it might be an audience of different interests and different backgrounds and the like. So I'm going to try to avoid being too technical. So if you expect a really technical talk, I guess we could talk offline. Is that, I hope that's okay with everyone. Again, if you want to leave now, the one thing you should walk away from the talk with is that no matter what the results, I think there are always really interesting stories. How people thought of the problem, how they solved it, how they didn't solve it. And I think those are really important lessons for all of us who are working on research in theory and in other areas. So I hope you agree. So let's get started. Okay. I thought I was really dead because my first joke's, but at least you get this joke. Yes, I am not going to talk about Galois descent lemma. Probably some of you know this better than I do. So this slide, if you would like, we can talk offline. You will not see any symbols like this again. Okay, thank you. Makes me feel a lot better. Okay, first thing I want to talk about is problems really, I always say this to students and colleagues, problems don't have labels. One of the things I think I'll say a little bit about education. One of the things we do with our students, or even ourselves, is we give them a theory exam to get into the PhD program. They may get a system exam. They may get an application exam, right? They get different exams. One time at Princeton, I have to tell you, I was running the grad program at the time, and we had a question on the theory question, on the theory part of the exam, like a 3-hour exam. Every theory student got perfect credit. Every system student got 0. And big surprise, on the next day, on the system exam, we had a question, guess what? Every theory student got 0, and every system student got perfect. So it's just flipped, if I said that right. And while we were arguing this among faculty, because this was going to affect whether people passed or not, I noticed the questions were really the same and had the same answer. So what was it's not super important, but just so you know, one question was graph theory. And it asked, how would you traverse a graph in linear time, basically depth first search or anything of that kind. And on this, that was the theory question. Theory students see graph, search, hit it out of the park. System students just, maybe it was, we weren't good educators at the time, I don't know. They just saw graph, panic, right? On the system question, it was design a garbage collector, right? This is a graph, really? You want to run in linear time and you want to mark all the nodes. It's really the same question. So anyway, it led me to suggest things like stop labeling questions on the call, and we didn't do that for a variety of reasons. But anyway, so I'll give you an example. You may not know this, and it's just an example of a completely non-theory question problem I once solved. I'm sure most of you don't know about this. So I won't give you the exact dates, but quite a while ago, this is a picture of Rich DeMillo. He was at the time at NSF, and I was on one of his panels, one of his advisory panels at NSF. Later, I was on the size advisory and others panels. This is John Hopcroft, kind of older picture, kind of fun. Of course, fame from Cornell as a theoretician. And at this meeting, John brought up and he said, look, to be taken seriously, computer scientists don't have a national meeting. We need a big national meeting. Chemists have it, physicists and mathematicians have it. The real fields have it, we don't. So we need to fix that. And that went over like a lead balloon, because the last thing we need is another conference. And I guess we still keep getting new conferences, but it was just not going to work. And I thought about this, who would go, how would we do this? Why would you send your best papers to this new conference, et cetera? So basically, I came up with this idea. John helped, we pushed it through. It became I guess we just had one this year, became the Federated conference. Have some of you been to the Federated conferences for theory, computing? So the idea that we came up with was just, why don't we take all the normal conferences and just co-locate and put them in the same place and do it roughly at the same time? And the big advantage is if your group only accepts one paper in 1,000, like some groups, and your group accepts them all, that's fine. But at least we'd be together. It looks like a national meeting, and that's continued. I think it's every 3 years. John and I get 10 cents a person per visit. Oh, obviously not. Anyway, I just want to give that as an example of thinking about other problems, thinking a little bit out of the box, and some interesting things. Anyway, I thought it was. Okay. When I say applications first, the yellow thing somehow announced new topics. This is obviously a wing for an airplane and a grid. I started to work on a problem at one time that I think will have some interesting stories. And this was what's called the Planar Separator Theorem. A lot of you probably know this. The idea is you take a planar graph, you can cut it into pieces efficiently. It leads, I'm sorry, I keep forgetting to click. It leads to a variety of very efficient algorithms. And there's a story behind it. That's what I want to share. So I was at Yale at the time, just starting out, and I had a proof. I don't know if you can really see this, but it's not my proof. I wish I'd kept my notes, but it was handwritten. Those were the days. And it was a really long proof, and it was complicated. And the time bound I got was n squared, quadratic time, which is not so good, but at least it was polynomial. It was a mess. I sent the paper to Dick Karp, who was a good friend at the time, of course, it still is. And I think he looked at it and said, I'm not interested. And he immediately sent it to Bob Tarjan. I think that was before he came to Princeton. Some of you may recognize Tarjan. This is an old picture of Bob. And Bob really loved this question, and he found the right proof. It was my proof, but fixed. And Bob's a world expert at making things linear, especially on graphs. He made up that question on the exam later on. And it has lots of applications, so we worked together on this. And I think it's kind of a nice example of how we came to work together and the like. And it connects to Stanford. So let me give you a story. I just can't resist. So you know who this is? So this is an earlier picture of Don Knuth, fame of his books. And I guess I'll put that up. His books, and of course, a inventor of tech. Probably not everybody knows. These are earlier pictures. I just decided to have fun. This is Richard Ladner, who started as a theoretician, has done some brilliant work early on. More recently has much more impact working on handicap, special needs, and disability access to systems. So probably he's done some more important work than all of us. But if some of you may know that, Knuth, of course, created this series of great books, and for a while, it was a long time to get the 4th edition out. It took forever. He thought it was going to come out soon, and just eventually became, of course, multi-part. Well, here's the story. I was visiting Tarjan. We had just proved the Planar Separator theorem, and it has a lot of applications. And I'm sitting in Bob's office, Tarjan's office, with Richard Ladner. We were both visiting for the day, for different reasons. And Tarjan said, I have to, excuse myself for a minute, and went out, I don't know, to get a drink of water or something. And in comes someone very tall, who is Knuth, first time I met him. So he walks in, and he says, I've been told there are 2 people here. One is Lipton, one's Ladner. So Ladner identifies himself at the time, and Knuth says, why are you here? And Ladner says, well, he was at Washington. I'm here to try to get some good PhD students. And Knuth said, wonderful, we have lots of good undergrads. Here's who you should talk to. And then he turned to me and he said, why are you here? And I said, well, I'm working with Bob Tarjan, with Bob on this nice theorem, and I started to explain some of the applications. Just then, Tarjan came back, and Knuth's first comment to me, actually, besides hello, who are you, or say hello, was, you've just ruined my lunch. And he walked away. And I could hear, those of you who know Bob Tarjan, he's a pretty easygoing guy. I could hear the 2 of them sort of arguing in the hall. And Tarjan came in and apologized. And of course, what had happened is, from Knuth's point of view, any advance in the field destroyed his draft of edition 4. So he would like us all to go to sleep. And we had the bad fortune of probably changing more than one section of volume 4, because we had lots of good applications. So I took this as a wonderful compliment, but I think Bob was more sort of amused, less amused that it was a great compliment. Anyway, I thought it was. So one more thing about the separator theorem. So it got generalized a lot. I'm not going to talk about that if you're interested. There's just been a huge amount of work on separator theorems, cutting things up into pieces. We noticed, and did not publish, maybe unfortunately, that if you had a graph of genus G, that means that it can be placed on a donut or things like donuts, where G is the number of handles. It doesn't really matter. That got improved to that. Now, we're using PowerPoint. Some of you may use some other systems. Some may remember when we had the acetates that you held and put up here, and you could do things with them that you couldn't do in PowerPoint, or at least different things. So this is for you. Yeah. You remember how we used to do this? Now, I can tell age. Some of you are looking at me like, what are you talking about? And Anna is dying of laughter. So, that was a really hard hack. No. I worked really hard on that. So you like that? I'll just do it again for you. But we used to pull these things down. It was just wonderful. All right. Around that time, Knuth, probably because of the separator, I'm sure lots of you have seen his books. He always wants your full name, right? So in my case, he wants my middle name. And like in our blog, we always want your full name. We don't do it middle initials. New York Times always wants your full name, right? So that's what Knuth did. He sent me a letter. And that's not the actual letter. I wish I still have a copy. It was only a couple of pennies. It was an old letter. And basically the letter said, I'm going to include you in the next edition of volume 2, and I really need your full name. We had no internet. You couldn't look these things up. He sent her a letter. So I wrote, I figured, what the hell? I love jokes. If you get anything out of this today, you realize I like jokes. Okay. I sent back a long letter, way before people cared about privacy, explaining how this is an invasion of privacy. And it was obviously a tongue-in-cheek. But it went on and on for a page that I just couldn't do this. And the letter was signed, you can probably guess, was signed, which is my correct full name. So I never heard a word from him but in the next volume edition, it was correctly in the book. So I guess he read it. All right. When I got the Knuth Prize, I actually sent him another. We don't usually correspond that much, but when I got the Knuth Prize, I sent him a letter thanking him very much and some other little jokes because his name is attached to the prize. I was very honored about it. And he sent it back to me with this extremely small writing that he does, correcting one typo. I was really embarrassed, and little comments all over it. It's available on eBay for $500. No, but it's very nice, I think. And these little tiny remarks, it's almost hard to read. Anyway, we'll move on. So another thing that I always tell my students and colleagues that I'll call, I think the most dangerous place in a paper, if you want to look for interesting open questions, is look at either the introduction or conclusion. Because a lot of us, and I've been guilty of this, you can be sloppy in an introduction. So sometimes people say, everybody knows this, because they're not really trying to prove it or verify it or test it. And then in the paper, they're very careful. But this is, of course, Richard Karp, a little bit older, less recent, what's the right term? Earlier picture. So we proved that circuits can imply Turing machine lower bound. Some of you may know this result. It's called Karp-Lipton, for obvious reasons. What was neat about it is that I can't tell you how many papers in the Boolean circuit area that we saw that said you can't do this. And I won't say that they had thought about it very deeply, because if they had, they probably would have figured out what we did. But they just thought it was just not possible. I think whenever people tell you something can't be done, if they give you a good argument or a long argument, like the halting problem, no, you can't do that in general. You can do it in specific cases, and you can do it in a lot of practical cases. But it is undecidable. I think you gave that lecture today, I believe, right? Okay, we all know that. But if they just say, well, it's obvious, or some throwaway remark, be careful. The other thing that was really cool about that paper, again, just trying to talk about some of the background, Karp wrote the last draft of the paper and introduced this P/poly. Those of you who are complexity theorists know that when you put a slash, it means you get certain advice bits. It's not really important. There's no registered trademark. It's another bad joke. But I really wish we got $1 for every time it was used in a theory paper, because we have accumulated a few bucks by now. Just the way it is. I couldn't decide if I was insulted or felt great, but in 2010, one of the big complexity conferences, or really the complexity conference, that is the conference on things like the Karp-Lipton, gave out tote bags. So this isn't the actual tote bag. I think it's as close as we could get. But it has the whole proof of our theorem. Now, it's sort of all symbols, and if you don't know what we're talking about, you won't follow it, that's okay. But the point is, your life's work is somehow on a tote bag. So I just can't decide, is this really cool and I should feel good about it? Or is this, I don't know, it was just fun. So high dimensions, I guess this is an attempt of just a picture off the web of what is a 4-dimensional object. A lot of people have really good geometric intuition. I do not. I'm really a more algebra person. Yet I've proved theorems, and indeed one I'm going to just state in a moment and show you a little bit about. You probably know, but I have really, really bad spatial stuff. I don't know why. This is David Dobkin, who eventually moved to Princeton, and we worked together. But we did this work at Yale, and this is our, I guess, famous search in high-dimension spaces. We showed that you could search a high-dimension space that was cut up by lots of planes in essentially not the number of planes, but log in the number of planes. So very efficient algorithms. I think that's a big surprise. I had no intuition. David, I think, had much better, but we were helped by a really clever and relatively high-tech method to help us visualize this. I'm not kidding. We actually used pieces of cardboard at least to get to 3 space, so we could see what was going on. But we eventually proved this all algebraically. And it's been improved in lots of applications. Let me show you, since I guess we need to have at least one attempt at a proof during a talk like this. So it's what people eventually became to call the slab method. So imagine on the left you have a graph in the plane, and you want to be able to search all those different countries that are in the region, or determine if a new point is either in one of those countries or outside. And you want to do it really fast. So you imagine, it's not just 20 nodes, but it has millions. So rather than doing it in a million, we can do it in log a million, which is the neat result. So the idea is to draw all these lines. Notice there's a line through every point, and then kind of think of moving them apart. Notice each, if you like, slab is now ordered. So that is, if you look at a slab, the points the lines actually are one above each other. So you can really use really simple search methods, basically binary search. And that's where the recursion comes in. That's one of the things that happens. So you probably know that, but if you don't, it took us a while to figure that out. And it generalizes, and there's quite a bit of work on that. But it was kind of fun to do that. So I obviously need to keep learning new tools. Hammer maybe isn't the best example. But when I was at Yale, there was a book that came out. It's a little hard to see. It was, we called the Little Blue Book. That's the publishing day. It was a big day in my life. And this was done by Erdős and Joel Spencer. And we immediately took the book and said, we have to learn this method. It's the probabilistic method. A lot of you know, if you're students or colleagues, this is where Erdős showed us that if you're looking to build an object, whether it's coding theory or circuits or other objects in computer science, one of the tools you should think about is pick a random object, and very often it has the property you want. Now the method's more subtle than that, and they wrote this book. It's, in some sense, a collection of papers they kind of stapled together, and it's a very beautiful book. There are now much better textbooks. Indeed, Joel is one of the authors of that. But for us, this was just a revelation. I mean, we had to learn this, at least for me. And we immediately created a seminar, and we decided to go through this line by line. And the book was hard to read, let me tell you. So I have to have some formulas, I guess. So probably a lot of you know, n factorial, remember, is, it's just n times n minus 1, etc. So it grows very fast, and this is the famous Stirling approximation, known for a long time, right? A lot of people recognize this, right? I mean, the Stirling approximation. So the book had this lovely phrase that Erdős would throw in, or Joel or both, that it would say things like, by elementary calculation, the following follows. And that meant, when I saw that meant either, okay, I'll get it in a minute, or I better get some. In those days I probably drank coffee, start percolating the coffee, because I'm going to be here a couple of hours at best, maybe worse. And indeed, there was one, I just had to do some fancy effect, one where you had to go out those many terms. And these guys, I think for them this is like 2 + 2 is 4. But for mortals like us, this took me a week. I mean, I kept adding terms and the calculators before we had good, symbolic packages. They were readily available. It was a mess. Anyway, we finally figured it out. Okay. But it led to an interesting story. So there was something called extendable hashing that was very kind of important at one time. This is Andy Yao, a good friend, of course, and a Princeton colleague for a long time. And that's Arnie Rosenberg, some of you may know. And what happened is I once did IBM, Arnie used to be at IBM, and I remember visiting him, and he asked me this question. I had no idea how to proceed. And I just forgot about it. Then a year later, I was visiting Yale. He was at MIT for a while before Princeton. And I saw him in a cafeteria. We were drinking some coffee and having some cookies or something. And I said, what are you working on? He told me this problem, which I didn't remember at first. It's the problem Arnie had asked me. And I said, oh, I had to solve that, because I had studied this book. And I said, well, bang, 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 random, probabilistic, we're done. And, it turned out to be a little harder than that. But Andy and I'd say within 2 days, had a full proof. There's actually a nice result that got, published and so forth. But what was interesting is this new tool made it, at the time I knew it better than Andy, which is hard to believe today, but anyway, at that time I did. And this new tool really opened the doors. If I was suggesting today, I think, quantum techniques, whether we can build quantum machines or not, a good example is there now lots of theorems have been proved using quantum methods, even though they say nothing about quantum computing. I'm right on that, right? I think that's correct. And that's also happened in crypto, right, Chris? So that's another new technique that we've talked about, a lot of us. Okay, another thing that can happen is we're always guessing, like, I'll talk about P and NP in a minute, but we're always guessing, does a problem go this way or that? And this is a picture of well, I guess it says it. So this is Hamilton, the inventor of quaternions. And I forget how many years, but I think he worked maybe it was 20 years, some huge amount of time of his life trying to figure out how to generalize complex numbers to 3-space, and you can't. It turns out it's actually really easy to prove that. But I think he never thought about that direction. He was absolutely convinced there would be a way to do that because he wanted the physics to be based on a nice algebra. And he eventually discovered how to do 4 dimensions. And once he thought of that, he built quaternions, and it was wonderful. We've guessed wrong, we meaning the field, lots of times. I'll just mention a couple for some of you who know these things. One is that non-deterministic space is closed under complement. People just guessed wrong on that one, including myself, and we worked really hard trying to prove the opposite. Bounded and polynomials, all these things I could talk about offline, but these are things we guessed wrong. And sometimes I argue with my colleagues. Of course, it's the proof's sort of in the pudding, but most people believe P doesn't equal NP, but if we've guessed wrong, we should be spending more brain power thinking about opposite directions. The same thing with factoring. I know Chris pointed him out, but he's working on it, not using factoring. But if you're building crypto systems based on factoring, maybe you should be guessing that factoring is really easy. Maybe it is. And if it is, you're in big trouble. Or same with lattices. We don't really know. Okay, this is fun. So this is the RSA gang in the wrong order. This is Shamir, Rivest, and Adelman, the famous RSA, Turing Award winners, great guys. In 1981, they sent around a paper, which I got, and it was how to play poker over wire and not cheat. I mean, obviously, there's lots of poker playing now on the internet. Whether cheating is occurring or not is another story, like it obviously is. But this was, provably, Ken Martin and I send and receive messages so that I deal the cards and I don't cheat, and Martin, doesn't peek at my hand and so on. And they had a protocol for doing that, and I broke it. And I think that was we still didn't really have good email, so it was an exchange of letters back and forth between myself and Rivest. And I should have challenged him to play because would have made some bucks. But rather than that, we just exchanged things until he finally said yes. Like at first he said, I'll change my rules this way. And I said, no, we can still cheat. I can't, at first I could not only figure out what cards he had, I could determine which cards he got. The ultimate of cheating in poker, right? The best thing is give you a really good hand, but not as good as mine. 4 kings, that would be a nice hand. Then he fixed that, so I couldn't determine what he got, but I could determine, I couldn't control what he got, but I could determine what cards he had. So that's a weaker notion of cheating, but plenty. But the thing that happened to me, Does anyone know who this is? Maybe this picture gives it away. I think he's called Tasman, and sometimes it was called Tasman the Navigator. So he did the following wonderful thing. And I've heard different versions, and maybe he didn't really do this. But one version is he sailed around Australia and discovered a whole bunch of islands, and perhaps including New Zealand, but he never found Australia. Now, I mean, it looks really like, I don't know how you do that, but so maybe it's not true, but I believe it is. But I feel myself a little bit like that. So I found this bug in this general crypto protocol, but I was at Berkeley and then at Princeton, and I really didn't want to work on crypto at the time for a variety of reasons. I should have thought very hard about this question, because it led eventually to semantic security, and Shafi, Goldwasser, and Silvio Bacali. They used to tell me, oh, we love that paper of yours, that's why we worked on all this great stuff, and they could add now, and won our Turing Award. So I'm like Tasman, I somehow sailed around and missed everything. Okay, so let me tell you something about something new. Now, I guess the picture doesn't look so new, because it's really based on some old ideas, like a lot of things, but it's really something new. We just started to work on, so I thought I'd share that with you in the next few minutes. I think we're doing okay on timing? So I'm not going to give you all the details because I don't want to do that right now, but I'll give you the high level. So a lot of you may or may not be chess players, but whether you are or not, you should know that computers playing chess beat humans terribly now. There was a time when people thought that was not going to happen, or it was going to happen, in 100 years. It's still not true for games like Go, although that's moving in this direction too. But right now, it's really bad. And this is, I guess, a picture off the web of a big data center. Well, unfortunately, it's worse. The computer you need to beat anyone, not just a weak player like myself, is small. Actually, your smartphone is probably capable of doing that using commercial software. Certainly your laptop can do that. So it's not even that the processors are filling rooms with special hardware. It's just a smartphone. This is sort of appalling. So it relates a lot of interesting, actually, theory questions. But just some things you need to know about. So there's a thing called the ELO rating. It doesn't matter exactly what that rating means, but humans right this minute, I talked to Ken Regan, who's my specialist on this. Right now, I think the best in the world is 2850. People have crept up a little over that. So that's just a kind of way to measure. The world champion, Magnus, is at 2850, I think, right this minute. Computers are at 3150. Some people think they're at 34, maybe higher, depends who you talk to. It's a little hard to know very precisely. The rule of thumb is if I'm about 200 or 300 points above you, then I'll win all the games. I'm sorry, I'll win the majority of games easily. So in other words, if a computer, your smartphone plays the world champion 10 games, the computer should win 7. It's just a wipe. So one side effect I'm not going to talk about is that this leads to a huge problem of cheating. We could give a whole talk, and you should invite Ken Regan. He gives a great talk on this. But people at some matches have their phone in their pocket. They've been caught with little devices. They go to the bathroom, and they have one behind the sink, other places. They have friends in the audience who, it's a big problem. Ken works on this a lot. Here's Ken Regan, who works on the blog with me. But here's an interesting question that we were involved with some group recently that got us thinking about the thing I want to talk about. So what if you add people to a computer? Does that help or hurt? So when I first heard this, I thought, no, I'm a really weak player. That's going to just be a problem. But it turns out the answer apparently is yes. They haven't done a lot of experiments, but about 7 years ago, there was a fairly serious experiment, and the human plus computer was going about 31, and the computer alone at the time was less than 3,000. So it was a little better. And my sense is, if you're a chess player, the machines are really great at take, sack, move, mate. They don't make mistakes. They don't get tired. They're not going to leave a piece where you can take it for free. They don't do that stuff like we do. But they're not very good at strategic positions. And perhaps the humans have been able to step in and help the computer in those cases. I mean, there's a lot of interest now in doing that. Chess is a good example, but probably the more general question is, we're going in the direction of AI type cyber things that will help us do all kinds of things, but maybe we're still around to help, that we have something we can add to the mix. Okay, so we made this into at least a kind of theory question that we're still thinking about. We know some results. So if you read crypto, there's always a picture of Alice. So here's the deal. Alice has a chess position, and I pulled these off the web. I mean, the real chess machines actually don't move the pieces robotically. I think the state of the art is they still knock pieces down sometimes, which is a problem, and other things. But obviously that will be fixed. But suppose Alice has, I'll go to the next slide. So let's make it more abstract. Suppose Alice has two chess machines. And she's, of course, the human. She has a board position. She's playing a game. She has a position I just showed you. She wants to make the optimal move, or not the optimal, a good move, right? She'd like to win. Let's assume it's a winning position for her. All right, does everybody follow? So she wants to, so she can ask, the first machine, well, what would you like to do? And it might say, do this. Then she can ask the second machine, and it will do something else. Because one thing about chess, a lot of games, is there might be two ways to win. There's not always a unique winning move. Now, if they both say the same thing, then in some sense her best strategy is to just follow that. But if one says do this and one says do this, how does she know which to follow? So this is George Palya. He always said, as a good problem-solving technique, try to make the problem you're studying as simple as possible. So the simplest version we could think about and solve, and we can do some more, which I'm going to just state in a second, is assume you have these two machines, and one is a perfect player. That is, it's just perfect. Right? It's not a high rating. It's every time you give it a winning position, it makes a winning move. Obviously, if you have a losing position, let's forget about draws. If you have a losing position, there's nothing it can do. It does the best it can or something. But if it's in a winning position, it always makes a winning move. But the other machine, in some single position of all the huge number of positions in chess, there's some position, for some reason, the machine makes a mistake. So it's a very, very limited mistake. But of course, Alice has no way of knowing that position. So she asks these two machines, what should I do? And again, if they both say the same thing, she's safe. But if they differ, what is she going to do? So she needs a way to figure out how to solve that kind of puzzle. And the thing I blitzed by was, after we figured this out, we thought it was related to these puzzles, some of you may know due to Raymond Smullyan, between what are called knights and knaves, where you have people that always tell the truth, and it usually has people that always lie, and you ask questions of them like, you'd like to know, well, are you a liar? Or how do I get to town? And you typically ask these complicated questions like, if you are a person who always lies, then which way would the other person tell me to get to town? And when you work all the cases, you get the right answer, right? You've seen some of these puzzles. But this is different. These chess machines, they don't know anything about logic. You can't ask them logic questions. You can just give them positions, and they'll tell you what moves. So we can actually handle this case. And in general, I'm not going to talk about how, it's not sort of that difficult. But what we can show is that even if it's one machine is perfect, but actually we could even do it when between the two machines, they make some number of errors. We can actually still relatively efficiently, I've left a term out, but basically that it's m times the length of the game, but in chess games are bounded in real practice. So what we can do is Alice can still win when she's supposed to win, which I thought was kind of neat. And we're working on the details of these things. Okay? So I have, what, maybe 5-10 minutes? So, okay, so we'll switch directions. One of my favorite, if you recognize, what is this, John Cleese? Anyway, so I want to talk about predictions. And I may skip a few slides to save some time. But I guess Yogi, unfortunately, just passed away, right? Yogi Berra. I always liked that Niels Bohr, the great quantum theorist from the early part of the last century, and Yogi, one of the great players of the baseball game. I guess we're allowed to talk about Yankees in this town, right? I mean, I'm a Met fan, so I'm not going there. But it's tough to make predictions, especially about the future. Predictions difficult, and so forth. So here's another one from a baseball player. Stengel says, what is it? Never make predictions, especially about the future. So I'll end with, what do I care if these predictions are wrong? What are you going to do? Okay. So anyway, I'll talk about a couple of areas. One is big data. And this is a great idea. I know I talked to people this morning to do this. You have a big team here. I think we have a lot of people at Georgia Tech. It's really a really interesting area. I mean, I've been working with people in this area of late. But here's an interesting quote, I think, at least for you to think about. I don't know if you all know this. So Rutherford, of course, is the inventor. Well, he's a Nobel laureate, right? Discovered, the atom structure. I always like this. It's a little scary, right? If your experiment needs statistics, you ought to have done a better experiment. I mean, well, obviously, we can't say to all large data people, please don't look at large data because you should do a different experiment. Of course not. But it does say that maybe we need to think about, I think, there's some really interesting questions here, that maybe we need to think or push back on the people that are giving us the data or collect better data or make sure we're getting the kind of data we really want. And anyway, so I don't really predicting that that's going to happen. Okay, privacy. So lots of people have been talking of late, everybody's breaking in, 20-some million people lost their fingerprint from the government. That's pretty scary if we use biometrics. It seems more scary to me than SSNs and other things. You can't change your finger. Well, maybe you can, but it's not something you want to do, right? So, so maybe we can protect systems. I mean, I sort of work part-time, at least in security at Georgia Tech with lots of people. We have some new stuff talking to people today about some new ideas, and that I could have talked about that today. I chose not to. I mean, just for fun, wanted to do this. I hope you're enjoying it as we wind down here. But what I have thought about, and I know some other people are thinking about, I don't know if anybody has any great results yet, but maybe we can focus on, we're going to lose information. Someone's going to break in and get some information about you. But is there something we can do to stop them from using the information in a way that hurts you? And just to give you some, these are sort of silly ideas, but to get you, if you haven't thought about it, for example, the reason SSN and social security numbers are so powerful is there are lots of ways we use that routinely to identify ourselves, even the last 4 digits. Well, if we stop doing that, then they're not all that valuable. There are ways we could do that. There are other examples of if you have a bad site to meet people with Ashley in the title, I won't say what the website is. You all know who I'm talking about or what website. Anyway, if you have a website you don't want to have people know you're on, and they get broken in, and I think 14 million people, something like that, were disclosed. Someone told me, should I repeat this? Well, someone said, someone downloaded here at Michigan the entire database and discovered, did you tell me the story? I downloaded it. So someone downloaded, you're the one. No, someone downloaded the whole database and discovered their son was on it.
That's me.
Oh, that's you. Thank you. Thank you, Peter. So, that's really interesting. But here's ideas that at least a few of us have been kicking around. What if you are compromised? What if I somehow try to release additional information. In other words, I make up phony records. So instead of 14 million, we suddenly have 28 million or 100 million. And they're just all mixed together, and some are real and some are phony. I mean, does that help? I think it might. You know, if you're a famous actor, actress, and say some bad picture is taken of you at a beach and you prefer it not to be revealed, well, there's not much you can do about that. I guess you can sue sometimes. But what if hundreds of, Photoshop pictures were revealed, that lots of them were phony, of course, and there was one real one. And you're CNN or the National Enquirer, and you want to decide, should you put this picture out? If you really don't know for sure, really, really sure that that's the Photoshop one or not, I know there are ways to tell them apart, at least people tell me, but suppose you do a good job of that in the future. I wonder if they would put it out, because if they put out the wrong picture, they are very much liable. So I'm just saying maybe there are ways to not necessarily think about this is never going to happen. I guess the analogy is sort of like, you know, the reason the Titanic was such a terrible disaster is they thought it was unsinkable, therefore they didn't have enough lifeboats or vests, therefore, unfortunately, many people were killed. You know, and you know, it's sometimes even called the Titanic effect, right? I mean, so think about that. Another one is compute speed. Just sort of end with, I think, one or two slides. So compute speed, you know, of course, we're hitting up against Moore's law. You know, that could be a whole talk that I'm sure you'd be interested to hear. You know, I'd be interested to hear other people even say what's up. But I'm not so much worried about that. What I do notice is that, at least for me, that the speed of data input and perhaps data output, but certainly input, has not changed all that much, right? I mean, smartphones, you know, it's certainly easier to click and move little icons around. But, you know, I'm not a great typist, but even if you're just typing in, you know, well, maybe it's worse, because now you're using your finger or two fingers or a pointer. But even if you are typing, you're not typing all that fast. So given, I don't know how many, you know, what we've gone up thousands or tens of thousands of fold in raw computing power, we've not certainly gone up even a factor of 100 in input power. You know, how are we going to fix that? I mean, it would be really cool to make that happen faster, I think. And you know, this is a really old machine. This is a new one. I'll stop. Last guess, you know, I do think that, I'm just trying to, I got like one or two more slides. I do really think this is true. We'll see. Something really strange. Okay, so here's my I'll just put it up, and this is the last essential slide. Here's a dream. I'd like to turn the tables. I think theory in general is really close to doing something like the following, that for a long time we've been sort of feeding off mathematicians in the sense that we use lots of deep theory from group theory and number theory and combinatorics and statistics to prove our theorems. And of course, there are lots of people that work in both areas, and it's hard to tell sometimes the boundary. But I don't think we've helped the other way. And it would be really cool, I think, maybe it's a long-term dream, but if someone could prove, these are just two ridiculously hard problems. One is proved and one is open, but it doesn't really matter. If there was some clever way to use computer science tricks, like Dan Bonnet and I have actually worked on this a little bit in the area of number theory, trying to use the complexity assumption that you can't factor rapidly to prove certain Diophantine equations have no solution. So we have some theorems like that that we're still working on. But that's the flavor of maybe could we solve some problem that the math group would say, wow, that's really neat, but do it by using computer science technology. And with that, I'll stop. And I guess that's David Byrne. Anyway, ask if you have any questions. I think at some of his concerts with 5,000 people, he yells out at some point, any questions? Which I always thought was kind of cool. So thank you very much this afternoon. I hope I didn't go too late. And I don't know, are there any questions? Let me know. Thank you.
They feel bad that they're having to prick the fingers of their kids 4 or 5 times a day. on average, you have about 1 teaspoon of glucose in your entire body. Put that into perspective. Try to measure 1 foot in 2 miles.